We're back with continuing to work through some review exercises for Unit 2A. In this video, we will go over the next 5 exercises, exercises 6 through 10. As in the last video, I would ask you to read the slide, with the question, pause, work it yourself, and then come back and check it. Exercise 6. Consider a gambling game where the player pays $5 to roll a single die. If it comes up as a 6, then the player gets back his $5 and wins an additional $20. If the roll is anything else, he loses his $5. Give exact answers as integers or reduced fractions unless indicated otherwise. A. What is the probability of winning? B. What are the odds against winning? C. What is the expected return in dollars to the nearest hundredth? And D. Is this a fair game? Press pause now. Well, the probability of winning is 1/6 because the only way he can win is when he rolls a 6. There are 5 other possibilities for a total of 6 possibilities. Equally likely, so the probability is 1/6. The odds against winning are 5 to 1. 5 ways of not getting a 6 to 1 way of getting a 6. Notice that a probability is a part to whole ratio, part to whole fraction, which could also be written as a decimal or percentage, whereas the odds of rolling a 6, odds of winning, are a part-to-part ratio. The part is of not getting it is first, and the part where you could get it is second. So 5 ways to lose to 1 way of winning. The expected return is the amount times the probability and then added up for the different possibilities. So there's 5/6 is the probability that you will lose $5. 1/6 is the probability that you will win 20. And you multiply those to get negative 25/6 and 26, and then add them together to get negative 5/6. If we put that into a decimal form, that's negative 86 cents. I take that back. That is negative 83 cents. Is this a fair game? No, the expected value is not 0. So notice this expected value thing works as a weighted average. You're averaging the losing negative $5 or losing $5 with gaining $20, but you're weighting them by the probabilities. Okay, so this says if you were to play this game over and over and over and over again, you would expect on average to lose about 83 cents each time you play. The only way for it to be a fair game would be if the expected value was 0. Exercise 7. Here we have what's known as a cross-tabulation table or contingency table. Notice that we have male and female, and then we have colleges for their majors, STEM, health science, or business. And we have some numbers here. So, for example, this 5 here says that there are 5 students who are both male and STEM majors. Notice that we have 3 students that are male health science majors, and 7 students which are male business majors. Those are in a row. The row below that, in the same order for the colleges, has the female students. So there are 2 female STEM students, 8 female health science students, and 4 female business students. Notice that those are intersections there. What this is asking you to do is complete the table to start with by figuring out the row and column sums for the frequencies, and then use that information to compute some probabilities. So part A says complete the table. then below it says use that information in the table to help find these probabilities. Part B, the probability that a randomly chosen student is a STEM major. Or in other words, what is the proportion of the students which are STEM majors? Same answer. C, what is the probability that a randomly chosen student is female? D, what's the probability that the randomly chosen student is female and a STEM major? Part E, the probability that the randomly chosen student is female or a STEM major. F, the probability that the randomly chosen student is female given that it's a STEM major. And G, what's the probability that the randomly chosen student is a STEM major given that the student is female. So let's work these problems out. Come back when you're finished. Press pause now. The probability that we have a STEM major is the total STEM divided by the total altogether. So I guess first we should add these up. We had 5 male and 2 female STEM majors for a total of 7 STEM majors. That's adding down that column. Add the column for health science. 3 male and 8 female health science majors makes a total of 11 health science majors. 7 male and 4 female business majors makes 11 business majors. 7 plus 11 plus 11 is 29 total students. So we know that the total numbers of each college there, each major. We can also do the total male by adding the 5, 3, and the 7 to get 15 male students. 2 plus 8 plus 4 equals 14, which is the total number of female students. And again, we can check that 15 plus 14 is also 29. Now, we can do these probabilities. So, for example, the probability of a STEM major is the number of STEM majors divided by the total, which is 7 over 29. So 7/29 is the exact value, approximated to 3 decimal places, that is 0.241. The probability that a randomly chosen student is female is the number of females over the total, which is 14 over 29. So 14/29 is the probability that a randomly chosen student is female. In decimal form, that is approximately 0.483. Those are examples of what we call marginal probabilities because they relate to events along the margins of the table. The AND probability, or intersection probability, is what we want for D, the probability that we have a female and STEM major. That relates to what the original numbers were. So female and STEM majors, there are 2 of those out of the total 29. So 2/29 is that probability, which is approximately 0.069. Female or STEM majors, here we have to be careful that we count all of these once, but not more than once. So the numbers we're adding up are all the females, which are 2, 8, and 4, but also the STEM majors, which are 5 and 2. But notice we want to be sure that we add those 2 female STEM majors only one time. So in this table, we're going to be adding 5 plus 2 plus 8 plus 4. Okay, that is a total of 19. An easier way to do that would be the STEM majors are already added up, so we could take the 7 there and add the 8 and 4 to it. Or probably the easiest way, the females have already been totaled up to be 14, just add those 5 male STEM majors to make 19. So either way you go, there's 19 of them. So the probability that you pick a female or a STEM major is 19/29, or approximately 0.655. So those probabilities were just straight probabilities. The next 2 are conditional probabilities. The probability that the student is female given that she's a STEM major. So what this is we ignore everything except the part we know, which is a STEM major. So you ignore all this part of the table over here. We only keep this one column of STEM majors. So it's the number of people that are both female in STEM, which is 2, over the total number of STEM, which is 7. So that probability is 2/7, which is 0.286. Notice it's different if you go backwards. The probability of a STEM major given female. Okay? Notice here that it is still 2 students who are both STEM and female. That goes in the numerator. But this time the denominator is the number of female students, which is 14. So we're restricting ourselves to the female row here. 2/14 reduces to 1/7, which is approximately 0.143. Exercise 8. Consider the experiment of randomly drawing 2 cards from a standard deck. Give exact answers in reduced fractional form and approximations in decimal form rounded to 3 decimal places. A. What is the probability that both cards are face cards if the selection is done with replacement? B. What is the probability that both cards are face cards if the selection is done without replacement? See if you can work this out. Press pause now. Okay, here's a hint. Use a probability tree and think of drawing one card and then the second card. In part A, you're drawing a card, putting it back, reshuffling, and then drawing the second card. In part B, you're drawing the first card and not putting it back when you draw the second card. If you haven't got it worked out, try again. Okay, let's see what you came up with. Did you get this? Here's a probability tree. I don't have the entire thing worked out in both cases, but I've got the important part worked out. So notice that you either get a success or failure here each time, which is what I'm calling this. So success this time is drawing a face card. So you get a success here, and then if you get a success again, then you're here. So this probability of this path here or down here is the one we're looking for. Now, how did I get these numbers? Well, what's the probability you get a success the first time? Well, there are 52 cards. 12 of them are face cards, so that's 12 50-seconds, which reduces to 3/13. That's the probability that you get a success that you draw a face card the first time. That's the same in both trees. Now, if you shuffle that card back in, you still have a 3/13 probability of drawing it again, drawing a face card again the second time. So that's 3/13. These are independent events. All of these probabilities of S's here, here, and down here will be 3/13. Multiply those together, and we get the probability at the end. Remember, this first probability is just the probability that you draw an S, or that you get a success, which is draw a face card. This probability here is that you get a success the second time, given you got a success the first time. In other words, that you draw a face card on the second card, given that you drew one the first time. Since these are independent events, these are the same number. Multiply these together, you multiply the numerators, multiply the denominators, so that's 9 over 169, which is approximately 0.053. Down here, it's exactly the same, except this probability here, the conditional probability, changes a little bit. Notice, since we've taken a card out, the denominator goes down to 51. Since the card we took out was a face card, if you're going up this branch, the numerator goes down to 11 because now there are only 11 face cards out of the 51 left. So the probability that you draw a face card, given that you drew a face card the first time around, is 11/51. So multiply those together, and you've got 11 times 12 over 51 times 52, or actually this reduces to 3/13 here. So that's 3 times 11 is 33 over 51 times 13. That actually reduces. 3 and 51 reduces there. So 51 is 3 times 17. So the numerator is just 11, and the denominator is 17 times 13, which is 221. So the probability we're looking for down here is 11 over 221. To put that in a decimal form, that is approximately 0.050. So those are pretty close probabilities, but they're not exactly the same. There's a slight difference there. Notice that if we had to find the probability of the success down here, where we had a failure the first time, we would still be dividing by 51 in this branch right here, which is the probability of success second time given a failure the first time. Denominator would be 51, but the numerator would still be 12 because there's still 12 face cards in there if you drew a non-face card the first time. Exercise 9. When the outcome of one event has no effect on the probability of the second event, we say that the two events are blank. Fill in the blank. List the three equivalent algebraic conditions for events A and B to be independent. Press pause now. Well, when the outcome of one event has no effect on the probability of the second event, we say the two events are independent. Algebraically, this means these three conditions. The probability of A given B equals the probability of A. Also, the probability of B given A equals the probability of B. And finally, the probability of A and B, or the intersection of A and B, that probability is probability of A times the probability of B. We've seen that if any one of these three conditions is true, the other two have to be true as well. Exercise 10. Suppose we have an urn with 5 red balls, 2 blue balls, and 3 yellow balls. We draw out 2 balls. Give exact answers in reduced fractional form and approximations in decimal form rounded to 3 decimal places. A. What is the probability that we get 1 red and 1 blue in either order if the selection is done with replacement? And B. What is the probability that we get 1 red and 1 blue in either order if the selection is done without replacement? Hint, do a probability tree. Press pause now. Actually, there are 2 trees, or at least parts of 2 trees we need to do. So we could either get a red, blue, or yellow. So there are 3 branches this time. And really, no matter what you do the first time, there's still a possibility of a red, blue, or yellow the second time. So each of the 3 branches has 3 more. The red ones here are the ones we're interested in, where it goes red, blue, or blue, red. And those are the only ones I bothered filling out, even though we probably could go ahead, well, we could go ahead and fill out all of these information in the trees if we needed to. But there's no point in doing more than we have to, I guess. So here we see that there are a total of 5 plus 2 plus 3, that's 10 balls total. And 5 of them are red. So the probability we get a red the first time is 5/10, reduces to 1/2. The probability we get a blue the first time is 2/10, which reduces to 1/5. And that's the same whether you're putting it back or not, because it's just drawing it out the first time. Now, if you're putting it back, the probability you get a red the second time is 2/10, again, or 1/5. And the probability that you get a red, probability that you get a blue the second time is 1/5. The same as a blue the first time. And the probability of a red the second time is 1/2, the same as the probability of red the first time. So these are independent events. In fact, all the reds would be labeled with 1/2 and all the blues with 1/5. Now we multiply along the path to get the probabilities at the end. So 1/2 times 1/5 is 1/10. 1/5 times 1/2 is also 1/10. And these are non-overlapping probabilities, so we can add them up. So these are both possibilities with 1 red and 1 blue. I said either order was okay. So you add those up, you get 2/10, which equals 1/5, or 0.2, or 20%. This probability tree over here on the right, when you're doing it without replacement, starts the same way. You have the same number of branches. They're labeled the same as far as the vertices go. And the probabilities here on the first are the same. It's still 1/2 for a red and 1/5 for a blue the first time. But the next time when we draw a blue, we're drawing from 1 less ball because the red one's gone. So one of the red ones is gone. That leaves us a total of 9 balls, 2 of which are blue. So that's a 2/9 probability that we get a blue the second time, given that we drew a red the first. Similarly, down here, if we draw a blue the first time, the probability of a red the second time is 5/9 because we still have all 5 red balls left, but 9 total. So that's 5/9. Multiplying these together, we get 1/9, multiplying these two. And these two, we also get 1/9. Here the 5's cancel, up here the 2's cancel. And so both of these are 1/9. Add those together, you get 2/9, or approximately 0.222. Notice that these are close, but not the same probability. Come back next video for the next 5 exercises.